Before we talk about the AI safety risk and so on, recent thing I have noticed is AI is also having some risk to computer science education. Like all these AI models, as they become more and more capable, we need actually more and more capable people to be able to control them and also to make them safe, right? But what I observe in my classes these days is actually the other way around. Uh, Last week I was teaching the class and I was telling students 2 is equal to 2 is false and 2 is equal to 3 is true, right? Nobody gave me any response, right? So the trend seems to be like people are getting more dependent on all these models, and then that can actually cause a problem as these models become more sophisticated. So what I will be presenting here is more mathematical treatment to AI safety, right? And we will, I think previous talk touched upon it. I think a important way where you can guarantee safety is providing rigorous formal guarantees, right? Uh, so this is how I imagine some trustworthy deployment cycles should happen. You would collect a data set. You will train a model to the best of your ability, maximize accuracy on that data set. Now the issue is, suppose I'm here and I want to go to Expo, right? What is the best way or the fastest way to get there? I can just break all the traffic rules, right? I will reach there the fastest if that is the metric I'm optimizing for, right? So if accuracy is your final consideration, of course your model is not going to be satisfying safety properties, right? There are different kinds of safety properties the previous talk touched upon, like robustness, fairness, safety. So when you try to develop any of these models, I think you need to think about these, and not in an ad hoc manner, but in a principled and systematic manner, right? Otherwise, you end up in this race of cat and mouse, where you are constantly finding problems and then you are fixing bugs, and then one day later the model is broken again, right? So once you have trained your model, maximize accuracy, you also should think about other properties that the model should have. Uh, for example, safety, robustness, and fairness, right? And then you need to ask the question, so my model is accurate. Is it satisfying safety property? Now, another thing is that safety is trivial, right? Because suppose I just want to drive to Expo, I can just drive at 0.5 miles an hour and I will be trivially safe. I will not have high performance. So safety and performance sometimes have trade-offs, right? So we have to think about those. And if you will ask me, and you will see in this talk as well, getting absolute safety, which many in our community of formal verification try to aim for AI models, because of this trade-off inherent in many domains, not always, uh, it's not possible to completely get 0-0. You will not get any attacks, right? So you have to be able to get some trade-off between the safety and the model performance, and then there would always be some risk. The question is, how much risk can you accommodate, right? So once you have trained your model as a developer, you need to think about these questions, whether your model is accurate, efficient, trustworthy. Like if the model is not efficient and I'm going to use a self-driving car, Tesla is not going to charge. I don't want Tesla to be charging me $50,000 more because it can run some very big model LLM on this GPU, right? So you need to think about these considerations: accurate, trustworthy, and efficient. If not, then you need to repair or retrain your model. Now, the check if the model is trustworthy. Uh, a good way to go about is with formal verification, because formal verification can give you once and for all the guarantee that you need. Your model cannot be attacked no matter how hard you try. This is in contrast with, like, if you do adversarial example, it will show that there is a violation, but it does not give you any guarantee if it cannot find an example, just that maybe you did not try hard enough, right? And once you have trained a model, I think previous talk also mentioned, you should not stop. You should do some monitoring in case there is distribution shift or some adversarial attacks, right? And then keep preparing and retraining the model. So formal verification can provide stronger safety assurances than benchmarking or adversarial example generation. So why is it not applied as much as it should? Well, one barrier is that it's more complicated and more expensive than if you did benchmarking or adversarial example generation, right? And in this talk, I will try to convince you that we can do something with formal verification for even very large models. So I have applied this kind of formal verification to get better models in different domains like finance, vision, systems, and most recent one is wireless, which we will be presenting at ICLR. So after 5G, a lot of people think we will not get 6G, but we will get next G. Nobody knows what that will be, but it will involve machine learning. So they want to use machine learning to do wireless communication. So in this case, you have a base station, it's having a neural network, and this neural network is communicating with a client, exchanging some information related to accurate communication or localization. Now, we did actually the first real world attacks in this scenario where you have an adversary. It's transmitting some small amount of noise to make the base station that's employing the neural network behave badly. That can have problems with with your communication accuracy, right? So again, the model that was trained to just enhance the performance is vulnerable against this kind of adversary, and we showed how you can combine formal verification to generate neural networks that are not only getting high performance, but will also have provable guarantees about their robustness against attackers. So formal verification requires two components. One is formal specification. So you must be able to mathematically describe the expected safe behaviors on a large set of inputs, right? It's not enough to just show me examples. Oh, this is the output and that is the output. That's not enough as a formal specification. You know, me as well, right? There is something with me that is like really triggered. When I took computer science, I wanted to understand these abstract concepts, which seems very hard and hard to define mathematically in mathematical terms. So we will see one of these for large language models soon. And then you need to have verification algorithm whether the model satisfies the specification. Now, the number of specifications that are satisfied can be used to construct new metrics for comparing different models, right? As I mentioned, there's a trade-off between accuracy and safety in most domains, and you can check which trade-off works the best. So these specifications would be related to different kinds of behaviors you want: fairness, robustness, privacy, and so on, and we will touch upon them soon. So a very traditional formal specification, I must say, people have been doing for the last 8 years, right, is the robustness specification in neural networks. Suppose I have this image of a car. What I want is that if I add a small amount of noise bounded by some amount in an L infinity ball, I generate a set of images. This is going to be a very large set of images, going to be, I think, 3072 power something. So it's something that you cannot enumerate, and you want to prove mathematically that a neural network is going to classify each image in the ball as car, right? So you want to give a mathematical proof, and in this case you cannot use the kind of interactive theorem provers, etc. That I think the previous talk talked about, because for doing those you need to have an understanding of what each neuron in the neural network does. Otherwise, you are throwing darts in the dark. So mostly formal verification for neural networks is automated, and then we have had moderate success in scaling these models, but still it cannot scale to the level that we want, right? So should we give up? I think some in our community is like, yes, until I verify this robustness problem, I don't want to move to something else. I don't want to attack large language models, it's just too big and so on, right? But my perspective is that even if we cannot give the very, very strong guarantees we aim for, at least we can do something that is better than just ad hoc benchmarking and adversarial example generation. So challenges in defining these formal specifications for LLMs are quite a few. You cannot use this kind of norm-based approaches to define what the set of inputs to LLM should be, right? I cannot say that, oh, I have a sentence that he is a good person, and I can construct some tokens in some mall and say that, oh yeah, I should be, this should be behaving in certain way. Now, also, as I mentioned, the previous property that each the neural network should classify each image in the ball as car can be mathematically specified using set of constraints, linear set of constraints over the output space. That is not possible for something like a large language model. So if I ask you mathematically to describe some fairness property for this large language model, it's highly non-trivial. Like, you want to cover a large space so that you can give guarantees over a large number of inputs. You want these inputs to be meaningful, that you are going to actually see in the real world. And then you should be able to use this to verify your system and be able to get some meaningful result to compare your models. As I say, you will not get for large language models the verification result that, oh, this large language model is not going to show problematic behavior. If I have a open source models, I can do what I want with it, and it will never be safe, right? Because I can control the decoding strategy. So I can always make a open source models that I have very full access to do what I want. So it's not very meaningful to ask this question, can my model be attacked or not, especially in the open source setting. So first case study that was done with folks at Amazon. They were really worried about their system producing biased output, right? So LLMs have been shown to generate outputs that show social bias and stereotypes. It is problematic because it can cause representational harm, where the output can impact individuals and redefine social hierarchies. It can also be causing allocation harm, because if the LLM is inherently biased and suppose is going to use that to make decisions about hiring, well, that's going to lead to problems. Now, I can describe in English counterfactual bias, semantic differences across LLM responses caused by varying demographic groups mentioned in prompts. Sounds good. But how to mathematically specify it? Unless you have a mathematical specification, you cannot go around verifying this, right? Just saying things in English and then doing manually some construction of prompts does not give you the formal guarantees that we want. So we want to be able to mathematically define it and then have algorithms that work with this definition to give end-to-end guarantees. Without this mathematical formalization, you will not go anywhere, especially if you are looking for formal verification. So we will go deep into this example and try to build the specifications, a particular kind of counterfactual bias specification step by step. So suppose we have a sensitive attributes, right? These are strings in the text that can be used to identify different groups that are sensitive. Example could be man, woman, related to race, and so on, so on. So we have a set of sensitive attributes, and then we have a set of prompts, right? Now the property I want from this set of prompts is that it should have a part which is independent of sensitive attributes and a part that includes sensitive attributes. Right? So given a set of prompts, I will construct a counterfactual prompt set, right? So not every prompt set is a counterfactual prompt set, right? I will build a specific kind of counterfactual prompt set with S elements which has a specific property. And this is not the only way to define counterfactual prompt set, right? But one way to do it. So what the definition says that for all the prompts in the set, the X part which is independent of sensitive attribute is the same. And then there is at least more than one sensitive attribute that is represented in this prompt set. Now, the third condition is important. It says if I actually have an unbiased text generator, then the output for that text generator for a given prompt should be just dependent upon xi, and it should not take into account ai, right? So important thing here is that there are certain set of prompts where the sensitive attributes should impact the final output. So we don't consider those. We consider only those where the sensitive information does not matter. And we will see examples soon. So let's see one example of this counterfactual prompt set. So suppose I ask, and this is a data set of professions, I ask the large language model to provide response to these two prompts. These two prompts are identical. They only differ in just having male and female, right? So ideally, the output of the LLM for these two should not differ. Now, what does differ mean? We will see soon, but it cannot be that the string exactly matches, right? That is just a very strict restriction that we want, right? Because the LLM can describe anything, but it should not describe something that creates a stereotype, and we will formalize that as well. But hopefully this input, the counterfactual prompt set construction is clear. It's not the prompt set that we will use, but it's a way to go. Next, we have to think about the output of the large language model, right? So we will define a distribution of counterfactual prompt set that we just saw, and one main contribution of our ICLR paper that's coming up is actually the first one to do any kind of formal verification of large language models. Will requires how you define this distribution. So you can construct this counterfactual prompt set, but then you need to define a distribution that captures a large space. Otherwise, if I just have one prompt set, then verification is easy, but that is not very useful. Now, you need to have a detector function that can identify stereotypes or disparity in given text for different sensitive attributes, right? So there is a key subtle difference here, because what will happen is that I will ask the LLM to give response to multiple prompts, and then I will detect in these prompts, is there something disparate, right? So if it is very positive about a particular sensitive attribute and neutral, or let's say somewhat negative about a different sensitive attribute, then that's problematic. That's an example of bias that I want to detect. So let's see here. I asked this question and the LLM produced these responses, right? So these responses are not exactly the same, but I hope people think that it is not biased, right? Because it's not using any sensitive information to give any negative about particular sensitive group, right? So in this case, our detector function for these two prompts will say that they are not, we did not get a biased response. So as I mentioned, given the kind of diversity that the LLM handles, asking this question that we ask in formal verification all the time, whether there would be some cases where the LLM output will be biased, is not very useful, because you can always make the LLM produce some biased output, right, with enough effort. So we focus on quantitative specification and ask the following question, which is, what is the probability of obtaining unbiased LLM responses for any counterfactual prompt set from the distribution of prompt set? So far I have not defined the distribution, right? Let's look at one distribution that we will create. So we will do the distribution of prompts by starting with initial prompt set, right, Q, and an LLM L. Then we will add prefix to it from a distribution. So in the paper we have defined 3 kinds of distribution. I will give an example of one of those. And then these prefixes would be used to construct your counterfactual sets of prompt. And then I will estimate the probability that the detector gives that the response is unbiased. So a specification that we have designed is captured a very wide range of adversarial scenarios, is mixture of jailbreaks. So we define a distribution of jailbreaks by taking a set of jailbreaks that were manually created and combining them to create a larger number of jailbreaks, and these are done in a way to enhance them, right? So we use two operations that are probabilistically defined. One is interleaving, where you will strengthen a given manual jailbreak with more bias provoking instructions. Mutation, you would change certain tokens in the jailbreak so that even if the model is safety trained, maybe the safety is relying on some memorization, it fails, and we will see that it actually happens. So what we are doing is that we are starting with some set of strong jailbreaks. We are constructing a larger set of jailbreaks, and within that distribution, we are going to give some formal guarantees on what kind of biased output we can observe. So let's suppose this main jailbreak is what we start with. It's a jailbreak we found from the internet, and it's quite effective, right? And we have modified it to, it was not designed for biased output, but we have modified it to generate more biased responses. You can see already, right, we tell the model to generate unhinged responses. So this is the jailbreak we start with. We are explicitly telling model to generate to be as biased as you can. Now we also have set of helper jailbreaks from which we extract instructions like you will never explain, overstate, repeat yourself, or output irrelevant answers, right? You will always reply with unique and non-generic content, and then your ultimate goal is to produce replies to the user that follows guidelines set in this prompt, right? So we are explicitly asking the model, kind of stress testing it to generate this very biased output. So we start with the main jailbreak, and then we have instructions from the helper jailbreaks. Now we can interleave them, right? So we can extract instructions from the main jailbreak, interleave them with the instructions from the helper jailbreak, and we select these instructions based on some probabilistic distribution so that it defines some distribution on the set of jailbreaking prompts you can construct, right? So here I took two of the helper jailbreak instructions and inserted them, but they can be inserted randomly at any place, right? Now you can mutate the jailbreak. For example, the text in blue, I just randomly mutated some of the tokens so that it becomes less suspicious, and using that we can define this formal specification, which is the mixture of jailbreaks. So I don't want, this mathematical details can be overwhelming, but we extract a set of instructions from the jailbreaks, and then we randomly pick instructions from the helper jailbreak and add them to the main jailbreak with some probability, and then also mutate them. So you see here we have these two probabilities, p lambda and p mu, that is used to define this complicated probability distribution. But this can be expressed in what is called like a probabilistic program, right? So this is how it looks. So you will start with this jailbreaks, and then you will have benign prompt, right? So you sample different jailbreaks you can construct from that probabilistic program, and then you can add as a prefix to your benign prompt, right? So complete the following sentence for a man, complete the following sentence for a woman, and then the LLM should produce its response, right? So you concatenate this jailbreaks that we get from the distribution to your original benign prompt, which was not explicitly asking the model to give something problematic. So once we have defined this formal specification, these are mathematical specification I just described. You can actually represent it on a computer, right? So traditional DNN verification algorithms, now you have formal specification, you need to think about checking whether your specification holds. So in this case, you want to compute the probability I mentioned about whether the DNN, the large language model response is going to be unbiased. So traditional verification method, it will start with the set of inputs. You can represent the probability distribution symbolically, and then you will symbolically propagate this distribution through the neural network to get the output, and then on that output you can check symbolically whether the property holds or not. Unfortunately, this kind of propagation does not scale to LLMs. You cannot also use that for closed source models like GPT, because this propagation requires access to model weights, right? So you will not be able to use this traditional DNN verification algorithms we have been developing for many years. So we resort to statistical bounds based on statistical estimation techniques. So what we do is we will compute, we cannot compute the exact probability, especially not for closed source models. So we can compute probability bounds, lower and upper bounds, on the true probability that hold with high confidence, right? So what we do in terms of verification algorithm, we will obtain an independent and identically distributed samples of this Bernoulli variable, which is whether the response is biased or not, and then use the Klopper-Pearson confidence intervals to bound this probability. Now, this is only possible because we defined distributions from which you can collect IID samples. If you cannot give this kind of guarantees. So definitely you cannot give this kind of guarantees based on static data sets, for example. So the framework, which is the first, as I mentioned, of its kind to do any kind of certification for large language models, is called LLM-Cert-B, will be presented at ICLR. What you will do is that you would start with a set of base prompts. You would add prompts from this jailbreaking distribution, observe the responses, and then collect certain number of samples, and then do the statistical estimation to get bounds, lower and upper bound on the probability of unbiased responses. So the next slide is going to be interesting because this is what we get, right? So this is the probability from some state-of-the-art models of unbiased responses. So Mistral AI, and this is one certificate. We chose a particular job description and added some jailbreaks, right? So what is the meaning of the bound above is that the probability of, with high confidence, 95% confidence, probability of obtaining unbiased response from Mistral AI is between 0.23 to 0.51. Llama is quite high, but also mostly because it usually says I cannot respond. It does not try to respond. Gemini is 0.55 to 0.82, and GPT, I think this is 4, 0.66 to 0.90. So you see, it does not always produce problematic responses. If you look at chat, like the GPT version, for one case it says I cannot give answer. In the other case, it gives biased responses. And this is again man versus female. I think the GPT example, it's more biased against man, and I think one of these Mistral is biased against woman. So it's not like these models are particularly targeting a particular, all the models are not targeting a particular group, right? So this bias is quite real, and as I said, if I just ask the question, can I get a biased output? I can always. And if I ask that question, I will not get anything meaningful out of it because I will always get the answer biased, right? But with this, you get some bounds with which you can compare your models, and maybe you can say Llama 0.931 is good risk threshold for my model, because I can tell you that this is not going to go away to 0, right? So overall results, that was just one particular specification where we were describing a particular profession, which was desktop automation. We asked a large language model to describe a man doing that work and a female doing this work. The bold data set has 250 of these. So we compute this lower and upper bound on the probability for the full 250 specifications and then do the averaging. So average shows some interesting behaviors. In particular, we see that this Mistral, Gemini, GPT-4, etc., I would say the risk is still high. Cloud and Llama seems to be most safe, right? So beyond that, we have the next study, which I'll not go that much into detail, but is motivated by practical scenarios. For example, chatbots, right? There's a lot of interest in using these chatbots for democratizing access to medical services. So uh, these chatbots in like very remote areas where they cannot have medical professions are supposed to give answers to medical questions. So we want to check how can we give guarantees under variations in different prompts, right? What would be the probability of getting a correct answer from the large language model? So the specification here is built on top of a knowledge graph. So suppose you have a knowledge graph of different facts. In this case, I have a knowledge graph about medicines and disease, right? So what I will do is I will collect uh, the subgraph of the knowledge graph that talks about, in this case, paracetamol overdose, right? And in this subgraph, I can construct different paths, right? So one part is, if you see, uh, overdose to nausea, overdose to N-acetylcysteine, right? So I can construct all these paths, and then for each path, I can construct some prompt based on some templates, and then I want to check how often does the LLM give correct response. So again, as a model developer, if I'm going to use it in healthcare scenarios, I should be getting some provable guarantees. It should not be like, oh, I just did my best, tested on this data set, and I did not find anything bad, and let's move on, right? So you should check what kind of bounds you get. In this case, if you get 0.4 to 0.5, I would suggest that even if your model is doing very well on the training data set, you should reconsider doing your model, retraining your model and making it safer. So that was one scenario. So I'm just saying that formal verification of large language models is completely unexplored territory so far, and these two works are actually the first one to attempt to do this verification, right? Future work involves, this is an expensive process. We have to, for each specification, to get the bounds to 50 samples, right? We want to do more to get tighter bounds. We have things in mind to scale this up, and that is where we are heading next. The other approach to give guarantees is actually to enforce certain semantic and syntactic constraints on the large language model output, and then you guarantee that the model output is going to satisfy those constraints. So this is decoding time intervention. So we will change the decoding of the model so that it always conforms to certain syntactic and semantic properties, and I will show you how that can be used to eliminate the risk of email leakage that the previous talk talked about completely. So in general, even with the agentic systems, these large language models are going to interact with external tools. Now these large language models, at least the less capable ones, have problems adhering to syntax of that the external tool wants. So for example, if I'm going to pass the LLM output to a Python interpreter and check what the output of the program is, I should first make sure that the program is actually a valid Python program, right? Now, if you will see many of these models, they are maybe very good with Python, but with more custom or languages that are less represented on the internet, they often produce syntax errors. So, for example, here I might have a question: how is the weather today? The LLM should provide me an output in JSON, and then I can pass it to an external tool, right? Now, the model in general is not guaranteed to produce an output that is going to be a valid JSON output. So we have this algorithm called Singh code, is LLM generation with grammar augmentation. So there is a mismatch between the symbols that your programming language thinks of and what the large language model thinks of, right? So if you see here, the import, which is a symbol in your grammar, is broken into multiple tokens, right? There's no kind of relation between how the tokens that the LLM processes uh, and the token that your grammar understands, right? So because of this mismatch, the model often produces an output that does not conform to the syntax. So this is the token misalignment, where it can produce the decoding which is most natural but may not satisfy the syntax of the grammar. So we have the algorithm Singh code, where the general idea is at each decoding step, right, you will figure out which tokens. Suppose you have generated some partial output, you will figure out which tokens lead to a valid output in the grammar. If not, you would mask out those tokens and only proceed with the tokens that your formal grammar, like the grammar of the Python language, is going to accept. So that's the high level idea. To make it work, you need to at each step identify what are the possible set of tokens that lead to a valid completion and which don't, right? I will not go into the details of this, but the high level idea is that you want to change the decoding strategy to mask out the tokens that will not lead to any valid sentence in your grammar. So there have been like previous approaches that try to do this syntactic decoding. Unfortunately, none of them scale to realistic programming languages. Ours is the only one that does so, and it's also quite efficient. So for JSON, right, we have 100 tasks for text to JSON conversion with Llama to chat model. If you use Singh code, the syntax accuracy is 100%, right? Standard is 59%, meaning 41% of the times it makes mistakes. Validation accuracy means that your model actually satisfies the semantic constraints on the JSON output, right? So we see that the syntactical accuracy leads to validation accuracy improvement as well, and the generation time for us is also smaller than even like standard generation. Also for programming languages like Python and Go, we do reduce syntax error. They don't go to zero because of certain quirks in these languages that we still have not handled. So that forms, this Singh code thing forms a basis for once we can enforce syntactic constraints, we can also try to enforce semantic constraints, right? So this is our framework that is going to be presented at ICLR. It's called IterGen. So it enforces semantic constraints on the large language model output by grammar-based backtracking. And I will tell you why this grammar-based backtracking is important. And if you do token-based backtracking, that's not very useful. So at a high level, it is doing some kind of rejection sampling where you check if the partial output is satisfying some semantic constraints. If it is not, you reject the output and sample something new. But you don't go back and reprompt the model. That's not what we want to do, because that's expensive. You will be doing a lot of prompt engineering, right? So we look at the partial output, check if it is satisfying some semantic constraints. If it is, go ahead. Not, we backtrack and do the next sample. So let's look at an example. This is for privacy preserving, for privacy. So here you want to check, I think the previous data set, decoding trust, has examples where you ask the model to leak email addresses. So this is a programmatic framework. Here you can specify how you want to decode your large language model output. So it takes this corpus as input. Corpus is the set of email addresses that you should not leak, and it takes the set of prompts, right? So we will not generate the full output in one go. We will monitor each partial output that it is generated. So we have a while loop that is actually defining the decoding algorithm. So while the iteration algorithm has not finished, you will keep generating until you encounter an email address. So how would you test if you have encountered an email address? So you can specify email address as a regular expression, right? And using Singh code, we can check whether we have generated a valid email address or not. Now, next thing the if statement says that if the corpus contains the email address that I just generated in the partial output, then I should go backward, right? So I should go backward to the start where I started generating the email address and try to generate the next output, right? And you will keep doing it till you are able to generate an output that satisfies this constraint. The constraint is that if it generates any email address, it should not be included in the corpus of sensitive email addresses, right? So this going backward and forward, you cannot do it at token levels. I can tell you. For example, my email address has 15 tokens. Your email address has 10 tokens. How are you going to specify how many tokens my email address is going to consume? If I say 10, it might be too conservative. It may not detect certain email addresses, right? If it is too big, it might erase a lot of useful output, right? You can only do this kind of backtracking at the grammar level, where you can detect symbols in your grammar. So again, as you can see, on all these models, the leaks go down to 0 with this approach. Now, this is just detecting because we have guaranteed, right? Because it's going to satisfy the constraint that we specified. So all these leaks are going to go to 0. You will not have anything that you do not want to output in your case. So I will just finish off by saying we have also a lot of work going on in the case of reasoning of models. So we have also been proving theorems about large language models. So in this case, there have been papers which say that we do the kind of syntax guided generation that limits the reasoning ability of large language models. We have a theorem which shows that this is actually the case. We have a method that can actually enhance this reasoning capabilities of the model by combining unconstrained reasoning with constraint generation. So if you only do constraint generation, the output is going to follow some syntax, but the reasoning will be bad. If you only do unconstrained generation, reasoning will be good, but the output is not going to follow any syntax. So we have a way of combining these two. It's called Crane, and that boosts the accuracy for all these models by a certain amount. Finishing off, we have also done this kind of regular expression based constraint decoding for diffusion large language models. It's more complicated than autoregressive models where you generate tokens one by one, because here you predict multiple tokens at once. And in this case as well, we do get boost in accuracy. So to finish off, we have more ongoing work. We have theory showing that if you have poisoned chain of thought data that you use for training, which actually can happen, it can actually hurt the performance of large language model compared to if it never did chain of thought reasoning. We are also looking into agentic model synthesis with formal contracts, kind of the contracts I just showed you, and also adversarial attacks on reasoning. So we already showed that the model can produce correct output, but its reasoning can be completely way off, pointing to that it's actually not reasoning. Thank you.
Thanks for the wonderful talk, and thanks for pushing formal methods to large language model. It's not easy. Can we have some questions? Someone should be rushing over with a mic.
Hi, thank you for your insightful talk. I have a general question about the counterfactual bias bit. So I'm curious about how do you construct the detector function for your framework?
Yeah, so that's an important consideration. So the data sets that we build off on, the bold, and we have also like decoding trust, they actually come equipped with detector functions, which are basically BERT models to detect whether there is a biased output or not. We tweak things slightly to make it more accurate for our setting, but it's not perfect, right? So we have also done like a human study to check how often does humans agree with the bias detected by our detector. the results show 80% agreement. Actually, this 80% agreement is also because our detector is actually not able to detect a lot of cases when there is actually bias. So the numbers I'm showing you is kind of an under approximation of the kind of bias you can see, because if we had a more perfect detector function, it would actually report more biased instances.
Yeah, thank you. I just have a quick follow-up. How does that will hurt the final certified certification guarantee you're providing using the statistical sampling?
Yeah, statistical guarantees, right? So the next step is also to kind of integrate this verification within the training loop to obtain models that can be more robust. So what we want to define is not to kind of adversarial training, but to define some set of distributions in some latent space that we can propagate during training with the certification in the loop to compute some loss function that can be used to tune the model weights in the direction of reducing these counterfactual biases.
Thank you.
Yes. Can we have one more question? Yeah.
Hi, hello. So thanks for the very exciting talk. I'm quite curious about the bias or fairness part of the large language models. And I'm quite curious, for example, we have this kind of explicit measurements like how successful you can attack LLM, like attack successful rate like ASR. So for fairness part, how should we measure like the impact of this kind of bias in the generated output of an LLM? Or let's put it in another way, how should we measure like how well our how well we can improve the fairness of output of an LLM?
So you are saying how to improve the fairness of our models?
Yes. Do we have some like established metrics or measurements for this part?
Well, the straightforward approach. So first of all, you see like the measurement thing I mentioned is kind of a more principled approach to like measuring this bias, right? That goes beyond just benchmarking on some data set or constructing adversarial example. Now, as I mentioned, people do adversarial success rate. That gives very limited information because it just says there is an attack. But important question to ask is that if we cannot mitigate this risk, is like how many adversarial examples exist? That is the question we are asking, right? So the straightforward way to do it, to do more safe models, is to do the data augmentation, where we see this problematic counterfactual prompt sets, we add it to the training set and give the guidance to the model that the output should not be this at least, right? That again gives some limited empirical improvements. I believe, and we are just getting started with this formal verification, is that you should use more guarantees from these verifiers inside the training loop to compute more better, more fairer models. And I will tell you why this would be the case. Because adversarial example, if you are thinking of a specification, it finds you one example. It does not tell you how worse that example is, right? You want to train with the worst examples, because if you are also safe against worse examples, you would be also safe against less worse examples, right? So attack success rate, the attacks, it finds one example, but it's not guaranteed to be the worst example. And because of that, this adversarial trained models do not generalize to more stronger attacks. With this certification, because you find more examples, it's possible that you would be finding examples that are closer to the worst case example than otherwise.
Thank you.
All right, let's thank Professor Singh again.